Hi, in this tutorial I will explain the Faraday law of induction and the principle of eddy currents. Faraday law of induction is important if you want to measure voltage. I created a test setup for this. I will show you that. So this is my test setup. What do I have here? I have a function generator that can produce a sine wave till 25 megahertz. I have an oscilloscope here. It's a 250 megahertz 4-channel oscilloscope. I have a current probe with a bandwidth of 10 megahertz. And I have 3 voltage probes with also a bandwidth of 250 megahertz. All these voltage probes have a short circuit. So this the probe 1 is connected to channel 1 on my scope, is the blue one. I have a short circuit on the black wire, and the other 2 probes have a short circuit on its own to the red wire. I draw a current by this 50 ohm feed-through termination. So what will you expect if you see this? According to the circuit theory, you will, because of the probes have a short circuit, you will expect 0 volts for all these 3 probes. We will look to my oscilloscope, to the screen of my oscilloscope, to see if it is true or not. This is my oscilloscope. What do I have? Channel 1, here the yellow one, is I draw a current of 115 milliamps, as you can see here. The blue curve, channel 2, is the probe on the black wire, and the red red on channel 3 and the green on channel 4 are the probes on the red wire, which are also short circuit. But I see now that I measure voltage, which is not logical, according to the circuit theory. I measure here voltages of 5 millivolts, 2.6 millivolts, 2.4 millivolts, so not 0 volts. And my operating frequency is 1 kilohertz from my signal generator. This is all based on the Faraday law of induction. I will show you something else. So the Faraday law of induction states that the curl of an electric field equals to the rate of change of the magnetic flux. This minus sign indicates that because of Lenz's law, the minus sign. So in human words, the voltage induced in a closed loop is proportional to the rate of change of the magnetic field that the loop encloses. I will show you these magnetic field lines and the current flow in my circuit, how they flow. So this is my circuit here. I will only look to the positive alternating part of the 1 kilohertz of my signal, so between 0 and 180 degrees. So suppose that my current is flowing like this. What do I have? If I use the right hand rule, so if you have a right hand, the fingers points to the direction of the field lines, and the thumb shows the current direction. For this, I created some small right hands. So if I have my current direction like here, flowing like this, what do I have? If I place my right hand around it, around the cable, what do I have? So my current is flowing here. You see that at the turn. So my field lines go into the table because my 4 fingers point towards the table. If you then still follow the current flow, so it goes through here to the 50 ohm, then goes back into the signal source. If I place my right hand around it, then what do we have? The thumb points my towards my current flow. The current flow is here, so my field also go into the table in this section here. Goes into my table. What happens here at my probes? What do I have here? So if I use my right hand rule, is that field goes here into the table. So if I use this, then into the table, so the current flows for my probe. The current flows towards my crocodile clamp. If I now look for the red probe, which is on channel 3, so what do you see here? The field goes into my table, so my fingers should point to into my table, and what happens then? The thumb shows that the current flows uh, flows away from my crocodile connector. So my current flows here. If I look now to this, what is the current flow of this? I will use this hand. So if the field goes in here, then it should goes out here. So field points in here, so the field should point upwards here, outside my differential circuit. If I do this, then I use my right hand. So what do we have? My field goes up here. That is also my direction of the fingers. So my current flows in that direction. So my current flows also away from my crocodile connector here. So this is if we look back to my oscilloscope picture. So what do we have here? Is the blue one is the probe connected to my black wire, and the red and the green are the probes. So show the induced voltage that are connected. The probes connected at the red wire. What do you see is that the blue is out of phase 180 degrees compared to the red and the green one. The red and the green are in phase, but the blue are out of phase. So the induced voltage is not the same. If we go back, so even the voltage amplitude, but also the phases are not the same. If we go back to my setup, so how is this possible? This is just because of the current flow. For this, the blue one, the current flows towards the crocodile clamp. And for the red and the green one, the current flows away from my crocodile clamp. You see that they flow away from here. And for the blue one, they flow towards the crocodile clamp. So the induced voltage here is not the same in phase. It's out of phase of this. These are in phase because the current flow is the same. But here, the voltage is not in phase compared to this one because the current flow is different. Here is towards the crocodile clamp, and here it's away from the crocodile clamp. That's the reason that you measure it's out of phase. So if you look, why is this this magnetic field, then it's here inside the table, and here it points upwards, so outside of the table. Why is this? I will show you. This is based on a Maxwell equation. I will show you. This is because of this Maxwell equation. Magnetic fields are always closed loop. So if you look to this equation, it states that the direct divergence of a magnetic field equals to 0. That means that magnetic fields are always solenoidal, meaning that there are no magnetic dipoles, no magnetic monopoles. They always come together. It's like the North, the South Pole, or of the planet Earth. This is different if you look to electric fields. If you look to an electric field, it's not a closed loop sometimes. So if you look here, um, an electric field always starts at the electrical positive charge and ends at the electric negative charge. And the voltage then depends on the path taken. If you look to here, what is the relation of the magnetic field strength H to the current? That is defined by this equation. The current equals to the integral of the of the magnetic field strength by the path taken. So if we go back to this means that what I explained here is that so magnetic field lines are closed looped. So if you go back to my test setup, when we have a closed loop, and it goes in here, so it goes up here. We always have a closed loop magnetic field line. If we go back to the Faraday's law of induction, I will show you this, which is this equation. So if there is no changing magnetic field, that means that there's no change of magnetic field, then this term is zero. This term is zero. So then we have a conservative electric field, implying that the voltage reading is path independent. Yes, it's path independent then. You can take whatever you want, path, you always have the same voltage. But in my case, here, in my case, I have here a big changing magnetic field. You saw that on my oscilloscope. I have a current. I'll show you. I have here a current. That's my current flowing. I have a current of 150 milliamps RMS flowing in my circuit, and I have which is changing. It's at 1 kilohertz, very low frequency, but it's changing. So this equation, so I have a changing magnetic field here. So if we look then to, I will show you something else. If I have a changing magnetic field, then we are in this case, and my voltage reading is path dependent. So we always have a different voltage reading. depending on where you place your probe, the area, all these things. If it's a time invariant electric field, then there is no changing magnetic field. So the E electric field is conservative and is equal to 0. And then it doesn't matter. You always will measure the same voltage. But that is not in my case. I have a changing magnetic field. So pay attention. The voltage readings can be different in value, but also the phase. If I go now, for example, this was all at 1 kilohertz. If I increase the frequency, I will show you first this. Yes. So if I change the frequency of my test case here, what will happen? You can, I will just change the frequency to 50 megahertz. And if you look to my oscilloscope, what I measure from induced voltage by the probes, and I'm now at 15 megahertz. I have to decrease the amplitude. So 4 volts per division. Yes. So what do I measure now? I measure higher voltages. So my the blue probe, which is connected to the black wire, and the red and the green, which are also a short circuit, but connected to the red wire. We measure an increase of induced voltage. You see it. Here are the values. So what happens here? I will show you something else for the explanation. What happens? If we look to the Faradays law of induction, um, here in integral form, but that's then here in differential form. I already explained this part, but so if we look, this it's based on this equation, and and then we will derive it further. So I already explained this. If we look, the voltage is equals to the change of rate of the magnetic flux. But the magnetic flux is based on the magnetic flux density B multiplied by the surface A. If we combine these two equations, then we get this equation. So we know that the magnetic flux density B equals to the permeability multiplied by the magnetic field strength H. This is then this equation. If we combine this equation and this equation, then we come to a new equation, this one. So what we know is that the derivative to time equals to a frequency multiplication. So if we convert this time domain thing to a frequency domain thing, then we have omega. So this d to dt time derivative must be replaced by omega, which is 2 pi frequency. And we are in the frequency domain. So everything remains the same. So we have a minus sign. Integral is here. the magnetic field strength H still here, and the surface A. And the permeability is also here, but d to dt has been replaced by this omega. I just take here the absolute value, but that doesn't matter. So an easy equation for this to know what is the induced voltage, what the probes will measure, is then from this equation to this equation, just this omega is replaced by 2 pi frequency. So to know how much voltage you will measure by the probe, induced voltage, you can use this equation. But this equation is only valid when the loop area is smaller than lambda. Okay, so I will show you something else. I have here an aluminum plate which has a high conductivity but is non-magnetic. It's aluminum. What will happen if I place this metal plate um, below the voltage probe, for example, then 4, and the green one? What will happen if I place this plate under the voltage probe? We are at 15 megahertz. I will show you that in my test setup. So I will first remove my right hand. If I first look to my reference, so at 50 megahertz, what is the induced voltage by this probe? I will first check on my scope. What do we have? So it's the green one. We have 15 millivolts. 15 millivolts. Do we measure now? If I go back to my test setup, so we have 15 millivolts. 15 millivolts at 15 megahertz without plates. Without plates. If I go to my test setup, so if I place now this metal plate below probe 4, what will happen? If I look to my oscilloscope, open the camera a little bit. Yeah. So what do I see? Now I go from 15 millivolts to 9 millivolts. Let's say you see that here, this one. So when I use my plate below my voltage probe, then my induced voltage, my measured induced voltage is lower. What happens here? If I if I go back, I'll first show you another test case before I proceed. If I do this, this was all at 50 megahertz, but if I do this at 1 kilohertz, I will do this the same thing at 1 kilohertz. So without plates, 1 kilohertz. What is my reference at 1 kilohertz? You will see it here. So I'm now at 1 kilohertz without plate. Then I have for probe 4, I have 2 millivolts. What will happen now if I place my plate under this, under the probe 4? I have 2 millivolts now without plate. And now I place my plate here. Yeah? Place my plate, and what do we have? 1.9. So it's quite the same. So it's also, let's say 2 millivolts. So we have the same value. What do we see? Why? So at 50 megahertz, if we use the plate, then we have a reduced induced voltage. But at a low frequency, in my case here 1 kilohertz, we have no change with or without aluminum plate. This is because of eddy currents. I will show you first. Oh, then. This is because of eddy currents, and here. Eddy currents, there are eddy currents induced in my plate now at a high frequency. At low frequency, no, because we measured the same voltage. Eddy currents only are applicable at high frequencies, higher frequencies, let's say above 10 kilohertz. So what happens if there is in my original test case? In my original test case, I will maybe it's better that I show you. Yeah, then here this. In my original test case, so my field went in here, went out here. So if there is a magnetic induction, so I have a field here coming up. If there is a magnetic induction on a conductive plate, so the field should hit a conductive plate, then the voltage induced in that plate, then there is a voltage induced in that plate because of the Faraday law of induction, which are already explained. This induced voltage on the plate, this induced voltage on the plate, this will create a current flow, and this current flow on the plate is called the eddy current. So there are currents, eddy currents, flowing on the plate. The direction of this eddy current will be such that its created magnetic field by the eddy current opposes the original magnetic field. So that means that I had my magnetic field like this, pointing up, but this, because of the plate, will be an opposite H field to the original one, so pointing down. So the total net magnetic field strength will be lower. So if this total magnetic field strength is lower, then also the induced voltage measured by my probe will be lower. This is because of this equation here. So my total net magnetic field strength here is lower, so my induced measured voltage is also lower. But this is only at, let's say above 10 kilohertz that the eddy currents will occur. So I will give you a summary of this. So to give a summary of this tutorial, the conclusion is that the Faraday law of induction, it states that the voltage induced in a closed loop, you need a closed loop, is proportional to the rate of change of the magnetic field that the loop encloses. An easy equation for a prediction of how much voltage you will measure added is that it's with this equation. So we have it's depending on the frequency, the permeability, magnetic field strength A, H, and the surface. If you change one of these parameters, then you also have another measured and used voltage. Eddy currents, they only occur when you have a magnetic induction on a conductive material. Then there is a voltage induced according to Faraday's law of induction. And this induced voltage creates a current flow in the plate, which is the eddy current. The direction of the eddy current will be such that its created magnetic field by the eddy current opposes the original magnetic field. Eddy currents only are applicable at high frequency, let's say above 10 kilohertz. And EMC, the preferable way is not to measure voltages because they are not uniquely defined. If you have a magnetic field, then that's here. If you have a changing magnetic field, then it depends the voltage reading on the path. If you don't have one on DC, then you always have a stable voltage reading. But so in EMC, we don't like to measure voltages. We prefer to measure current because currents are well defined. If there is no alternative for voltage measurements, then you have to protect against these magnetic fields. How do you do that? So for low frequencies, we have seen that the eddy currents, they do not work. It's only at higher frequencies that eddy currents work. So for lower frequencies, you have to reroute the magnetic field so that the magnetic field doesn't go into your will not be picked up by your voltage probe. So you reroute the magnetic field just by using a box, a material with a high permeability. If you have a high frequency circuit, so above 10 kilohertz, then you can what I explained here in this session is you can use a conductive plate. So then eddy currents will be generated, and then your total magnetic field strength will be lower. So then you have a more stable voltage reading. Or you place it in a Faraday cage. So magnetic fields cannot be picked up by your voltage probe. This was my tutorial about Faraday law of induction and some examples, and also eddy currents explained. Thank you for attending this tutorial.